Monday. I'll be the chair. Our first speaker, Neil Balmforth, plastic indentations. 40 minutes,
Okay.
including questions.
Okay. Thank you. Good morning, everybody. I made up a couple of words on this slide. Plastic indentations into a plastic material. That's what this talk is about, but plastic indentations sounds a little bit snappier. I also made up a collective noun for two Hewitts. I had the opportunity to work with two excellent Hewitts, Duncan and Ian, and I thought I'd call them a splendor of Hewitts. My other collaborators are J and T, Jim and Thomasina. Okay, so I'll tell you about three problems in which you're pushing something into a plastic layer. The problems is going to be a locomotion type problem, a problem of forming footprints, and then finally I'll mention something about creating washboard patterns. Okay, so let's get going. So I just review a little bit about ideal plasticity. So I'm thinking of a two-dimensional problem, and I'm going to throw away inertia. Gravity could be acting, and I'm thinking about a perfect plastic material. Okay, so I've got force balance, which tells me something about the stresses. Sigma ij are the stress components, and in the confines of ideal plasticity with the von Mises yield condition, I split the stress up into a mean pressure and a deviatoric stress, and the deviatoric components of the stress satisfy that yield condition. Tau y is the yield stress. All right, so I'm going to be focusing on material that's deforming with that sort of a constitutive law. One of the things you can do with this set of equations is to rearrange it. I can conveniently satisfy this yield criterion using this angular variable theta, and if I take this, throw it into the equations, rearrange them a little bit, I can find these two equations down here, which establishes that this is a hyperbolic system. These are the characteristic equations, and there's two families. The characteristic curves in this case are orthogonal, and they're traditionally called sliplines in plasticity theory, the alpha lines and the beta lines. So that's a bit of classical plasticity theory. Now, in the 1920s, Prandtl wrote down two exact solutions of these slipline equations. One was for the indentation of a flat plate into a plastic half space, and the other was for a squeeze flow problem where you have a material confined between two plates and you're squeezing them together, or equivalently you're pushing one down onto the other one. So let's just look at the solutions in a bit more detail. So this is the squeeze flow case, and you've got this infinite layer, you're pushing down on the top, and in this particular case the families of the slip lines, they correspond to fixed curves. So you get these repeated curves as the blue lines and the red lines of the two families. In the case of an infinite layer, you imagine that you've got some plane of symmetry in the middle, and for this type of solution you can satisfy the symmetry conditions by inserting two little plug regions in the middle. In plasticity theory, you can usually take any one of the slip lines, any one of these characteristics, to be a yield surface, the border between rigid and deforming material. So what you do in this particular case is you take a pair of slip lines right intersecting the midline, and above and below you say those are rigid blocks. So for example, this one's just sitting there on top of the bottom plate, and this one's moving down with the top plate. Everywhere else things are kind of sliding sideways, and so where these characteristics are meeting the top plate, then one family meets it in an angle of 0, which is characteristic of the fact that here one envisages that you have smooth plates, and so the material is sliding over the top of it. So that's the squeeze flow type Prandtl solution. And then the other one is this punch type problem. I've got this half space, I'm pushing a plate down into it. The slipline pattern is rather more complicated. There is a a problem, an inconsistency between the boundary conditions at the edge of the plate that you're pushing in order to reconcile the two sets of boundary conditions. One inserts a little centered fan there, and then you add these triangular regions of constant stress. So in this particular case, the free surface conditions on either side demand that the characteristics come in at 45 degrees, and then the triangular region underneath is consistent with the idea that you have a rigid triangular block that's just descending at the speed of the load that you're imposing here. And it's basically held at the yield stress. So material comes down vertically, then gets diverted sideways and comes out the sides. Okay, so those are Prandtl's two solutions. There was a sort of an intermediate solution that was written down by Salençon in 2002, 80-odd years later. And so you see half of it here. It's a combination of the two. You sort of somehow fit half of this on the edge of that. So you have the triangular region here adjacent to the free surface. That's sometimes called a Rankine zone. There's an expansion fan, and then you build the characteristics to the left from here, and the slip lines you integrate along the characteristic curves. Ultimately, after a short distance, they converge to these fixed characteristic curves of the squeeze flow solution. Those are cycloids. So they converge to the cycloids when you get a sufficient distance from the fan here. So those are some convenient slipline solutions from plasticity theory, old and new. And so what I'd like to do is I'd like to show you how they come up in these three particular problems. Okay, so the first one is this locomotion problem. There's a classical paper by Taylor in 51 which talks about achieving locomotion through a viscous fluid by having a flexible sheet down which you force waves of a given shape. So there's been a lot of interest in that more recently, where the material around the swimmer is not a viscous fluid but a more complicated kind of fluid, a complex fluid. So I'm going to be thinking about this particular problem where I have a yield stress fluid surrounding the swimmer. Okay? So this is going to be the viscoplastic version of Taylor's swimming sheet. Now, I'm talking about these plastic problems. In this particular case, what I'll be thinking of is a Bingham fluid. A Bingham fluid is something that's got a plastic stress and a viscous stress on top of that. In the limit that you are dominated by the viscous stress, that means you get back to the viscous fluid model. And in the limit that you're dominated by the plastic part of the stresses, you head towards the plastic limit, which is this plastic, one of the plastic problems that I'm telling you about. So using the Bingham fluid bridges between those two limits. Okay, so a little bit more about the geometry. Following Taylor, you kind of consider only half of the problem, the upper half, and you consider a periodic section of the flexible swimmer. So here's the domain. You've got a periodic domain. You've got this surface on which I'm going to be putting waves of a prescribed shape. Okay, and they basically push on the material to propel the swimmer. In this particular problem, you're generating stresses at this boundary, and they decline as you go up. And ultimately, you will definitely fall below the yield stress at some point, and then it plugs up further away. So you can hide a boundary in there for doing computations. It doesn't matter where the boundary is, provided it's in the plug. So there will be an upper plug for the purposes of practical computations, but it's not important. Okay, so let me just highlight that I'm going to neglect inertia and gravity. I'm considering this simple periodic section. And I'm going to be fixing the transverse displacement just as a sine wave. So as I mentioned, the upper part plugs up. What that means is that there's a localization effect. The yield stress localizes flow to within a short area near the swimmer. And you see that in these numerical solutions. I'm not going to show you any more details of the calculations. These are numerical computations that we've done. And you see the swimmer down here, so it's a relatively low amplitude. It's sending waves down it. The lines here are streamlines. The shading is the strain rate. Where it goes black, that means it's rigid. Okay, so the interpretation of this particular picture is that you have yielded fluid next to the swimmer and it plugs up there. There's a yield surface here. Okay, And the three pictures correspond to increasing the strength of the yield stress. This one is very close to the viscous limit. This one is dominated by the plastic stress. And as you see, as you increase the yield stress, you localize motion closer and closer to the swimmer. Okay? In this particular limit, it's very close to the problem that Taylor considered, which is low amplitude viscous fluid, and you can read off the swimming speed is there. In the formulation of the problem that we've used, the swimming speed that Taylor derived corresponds to this. K is the wave number of the sinusoidal waveform here. A is its amplitude, C is the wave speed. So that's the speed that you would get with the way that we formulated the problem via Taylor's analysis. So as you go up here, this corresponds to the plastic limit. The question is, what's the wave speed in this particular limit? And you might also wonder, what's this sort of pattern that's forming there? And maybe it looks a little bit familiar. Okay, so here's Prandtl's punch solution again, and I've just turned it upside down. So this is where you're pushing on it. You've got those two fans and then the three triangular regions. If you imagine just cutting the sides of this off and then periodically repeating, that looks a bit like that solution we were getting in the swimmer problem, and indeed that's exactly what you get.
Would you mind telling us a little bit more about how you solve this numerically? Because you don't know where the stress boundary is, right? You have to.
It's a complicated nonlinear boundary problem of some form. It's a stress boundary. There is some variational. Do you really want to? Can I tell you that at the end?
Right, no, I don't want to.
Okay. All right. Okay. It's not straightforward. Okay. Okay. So this is the solution to which those numerical solutions were converging. All right. And this is a slipline pattern that you get from it. So you've got constant stress triangles, fans, just like in Prandtl's solution, except that it's periodically repeated. So what you can do in this particular case, you've got the stress solution from this slipline pattern. You can also go now and look at the equations for the velocity field. The velocity field is also hyperbolic. It's got characteristics. In fact, they're the same characteristic curves. So you basically can take the known velocity boundary condition on here and propagate it up along the sliplines to get the velocity field everywhere. If you do this in the frame of the swimmer, that means you have a given boundary condition here of transverse motion and no longitudinal motion. By the time you get up to the plug here, you get a constant plug speed, which is the swimming speed. So that's how you calculate the swimming speed. And if you examine this thing analytically in the limit that the boundary is essentially flat, that's the low amplitude limit, you can analytically calculate what the speed is. The exact analytical form is not important. The interesting thing is that it's exactly twice the speed that you get from Taylor's calculation. Okay, so this is just showing you the streamline plots. This is now in the frame of the swimmer, and there are two sets of curves there that are on top of each other. Those are the analytical solutions that you get from doing this slipline calculation compared with the large yield stress limit of the numerical computations. Okay? Okay, so you can go way beyond this. We can do different kinds of swimming strokes. We can talk about longitudinal waves. So I've got a swimmer, instead of deforming this way, it's deforming in plane like that. In 68, Tuck did the parallel of Taylor's problem for that and found a swimming speed. It turns out, somewhat magically, that once again, if you do the viscoplastic version of this and the plastic limit, you get exactly twice the speed. You can go and you can talk about what happens at intermediate yield stresses, somewhere between the two limits, what happens at higher amplitude, and you think about things like efficiency. However, I'm going to leave that problem now and go on to the next one, which is about footprints. Okay? So, yesterday we had a talk by Shreyas where he mentioned sort of evolutionary biology and the development of the foot. So people try and infer things like that from looking at footprints, and in particular they like to infer things about dinosaurs. And so there's quite a vast literature that's built up about inferring things about dinosaurs and later creatures from looking at their footprints. And there's a sort of a vague principle that's always used, which is that somehow the weight of the animal is proportional to the depth of the footprint. You might wonder whether that's a sensible thing to even think about, given that there could be a many different set of complicating factors. People have looked at this thing from the perspective of experiments. They've done indentation studies where they've pushed things into various substrates, plasticine, mud. They've even sawed off emu feet and done it with those. And there's been some computations where they've basically solved a plasticity problem with finite element methods. It's sort of a classical kind of indentation problem. Okay, so it's clear from all of those that there are a lot more factors that influence footprint depth besides the weight. Okay, but what I'd like to do is I'd just like to build a sort of a much more simple mathematical model to understand the general ideas of how you find, how you create a footprint. Okay, so first of all, I need to say what I mean by walking. Okay, so I'm going to follow Shreyash. Right, so let's assume that there's two phases to the footprint. So first of all, I'm going to come down. Sorry. So I'm going to come down. I put my foot down and lift the back one up. So I'm exerting a load. So there's a first phase, the descent, when I'm on one foot and I'm exerting a vertical load. And then I put the other foot down and I bring this one up. So there's a second phase when I raise at constant rate. So I'll sort of envision the process as being a descent and an ascent, the descent at a given load and the ascent at a given rate. Okay?
Do you have a no-slip condition on the foot?
And, well, we'll talk about that. Okay. Oops, the daisies. And action. Okay, so the descent first. So to begin with, I'm just going to consider a shallow layer of plastic material, and I'm going to be indenting it with a foot. Okay, so let's assume that it's a relatively shallow layer to begin with. So this will simplify things. One can do a lot more analytical calculations in this particular limit, and what happens underneath the foot corresponds to a larger degree to Prandtl's squeeze flow type solution. Okay, so if this is a shallow layer, then there are some simplifications of the force balance equations that I can make, and I can actually end up solving for the stress components analytically rather than going through slip lines. So let's quickly look at that. So you assume that the pressure dominates the deviatoric stress components and that the derivatives in the horizontal are much less than the vertical derivatives. So this is a sort of setting of classical Reynolds lubrication theory, where I'm just doing it for a plastic material rather than a viscous fluid. Then at the bottom here, there's some rigid boundary. There's a foot here. On both of them, I impose some stress conditions that correspond to having these sliding conditions. It's the same that we had in Prandtl's squeeze flow problem. Right, so there's some slip conditions that correspond to these surfaces being assumed smooth. That's what happens underneath the foot. Outside, I've got a free surface. I don't know where it is. Let's just say that the free surface is at position H. It could depend upon X and T. And the surface is free, so you say that the pressure and the shear stress is 0 at the top. So given that, we can solve for the stresses, or in particular the pressure and the shear stress underneath the foot. Right? The pressure is hydrostatic. Big P here is the pressure on the bottom of the foot. You can take that, you can put it into the other equation and find that the shear stress looks like this. And the boundary conditions, the shear stress conditions on the top and the bottom, then tell you what the pressure gradient is in terms of the yield stress here and H, that's the depth. Right? There's a gravitational bit and a yield stress contribution. Right? So this is the analytical simplicity afforded by lubrication theory here. So with this pressure distribution, what's important is that you can go and calculate the force on the foot. So the integral of the pressure over the foot, that's going to be the upward force. With a little bit of integration by parts, I can cast it into this form and then use this. So there's going to be a yield stress part and a gravitational bit. Okay, so HL here, that's going to be the depth at the contact line. So let's just go back here. So we have a foot, there's a contact line at the back, contact line at the front. And just for simplicity, in all of this analysis, I'm now just going to say that it's left-right symmetric. So it's not like the Monty Python foot. Right? Left-right symmetric. So I'll only think about half of it. So you can calculate the lift force. That's the main piece of the analysis. Okay? If you don't like doing the shallow layer under lubrication theory, you can actually think about doing a relatively flat foot and a deeper layer and using those slip line solutions that I showed you before. if you do that, then you can calculate the force on the foot, and you can go from the deep limit to the shallow limit using that sort of bridging slipline solution by Salenson. So there's a sort of lift force that you'd expect for the deep limit, that's Prandtl's punch, and then there's a lift force that you'd expect for the shallow case, that's basically Prandtl's squeeze flow solution. Okay, so the main thing is that we can use that plastic indentation stuff to calculate the lift force. There's a little bit more that you need to do in this particular case. You squeeze fluid out and you've got that free surface on the left and the right. So there you can go back to the force balance equations and you can integrate those again. So once again the pressure is hydrostatic. You can then get the shear stress and then the boundary conditions on the shear stress. In this particular case they give you an equation that you can solve for what the free surface shape is, which I've written down here. So that says that the free surface is given by this parabolic shape at x equals L, the contact line. I've got a known thickness. Okay, and actually, incidentally, this solution is exactly the same as an early solution for a glacier by Nye. Okay, so underneath the foot, I have a known profile, right? I know the shape. I just don't know its exact position. So delta here is the height of the foot. Eta is the shape of the foot. And when I get to the contact line, I have a certain depth given by this. That feeds into here. Then if I go and I look at what I have, ultimately when I demand mass conservation, what I say is that the integral of the height over the whole deformed region is the same as what it was to begin with. So if h0 is the initial depth, h0 times the length of the deformed region has to be given by this combination of the integral of the h underneath the foot and of the deformed free surface. That's really just an exercise in matching areas on a plot, which is done here. So imagine that you've sunk to a depth here, and this is your foot, this is your free surface. I've just got to adjust this particular point so that area matches that area. That's all we're doing here. Okay? So you basically calculate that contact length given the depth of penetration. And given the depth of penetration, then you can calculate the lift force on the foot. And so if you then want to understand how much you sink in, you can go to the equation of motion of the foot. You've got a load, that's the lift force. So by Newton's law, you can solve this to get what happens when you let the thing go, just first of all making contact at t equals to 0, and then sinking in. Okay, actually one important thing, it looks a bit like an oscillator type equation, a nonlinear oscillator, but it's not, because when you start to push in, you slow down, at some point you stop. As soon as you stop, the squeeze flow turns off, the layer solidifies and locks into place. Right? So you only use this ODE up to the moment that you stop, and then everything just halts. Okay, actually what you can do is you can just integrate this by introducing a potential for this lift force, and you can relate the initial speed at which you make contact to the final depth. Right, so clearly the final depth depends upon the initial speed as you're walking, as it should. Right, so there's a model here for how far in you go. That's the descent. What about the ascent? Well, there are a number of things that could happen depending upon the conditions on the underside of the foot, which goes back to, you asked me about no slip, about what you assume happens underneath the foot. So if you're thinking about something like sand, then when you press your foot on it and you descend, when you lift your foot up, you might think that you instantaneously detach. There is air available to fill the gap. There's no problem with just lifting off. The material doesn't necessarily support any stress under tension. Right? You just effortlessly lift off. And so if you did that, then you might think that the pattern that you imprint is just what you would get from having pushed the indenter into it. There's a slight complication, which is that the inner edge here, right, may be unsupported, and so there could be a further collapse that occurs as it avalanches back into the hole, into the footprint. So that's what's happened here. We started out with the indenter and the free surface. You then detach. You assume that there's no contact there afterwards, and then there's a little bit of a further collapse back in to give you this profile, and this is another exercise in matching areas. Okay, so that's what might happen if you had a bunch of sand, and it's what you clearly observe when you're playing around on the beach with dry sand. A different alternative is if you're somehow limited by the availability of air. right? You can't instantaneously detach because you've got to get the air in there, and then the only places that you can detach is from a contact line. So in that particular case, things are a bit different. So we start with the same initial condition, and then there's a contact line there that starts to migrate in, and material collapses back in as you're lifting it up, but underneath the foot you're still attached. So in that particular case, there's a reverse squeeze flow. You suck material back in, and then at some point you do lift off when the contact line gets all the way in there. Right, so there's a sort of a second possible situation where you're limited by the availability of air. Right? And with things like wet sand, you certainly do see that. If you go to the beach and you stick your foot in the sand and lift it out, you'll see that there's some sort of, the depth to which you went in is not the same as the final depth, because clearly materials get sucked back up. Right? So in option A, it's the descent that determines everything. In option B here, it's a mixture of both the ascent and the descent. And then there's also a third situation, which is that if you had a true no-slip condition, something very, very awkward might happen, which is that you're forced to stick to the top surface. So it's like the peeling problem of McEwen and Taylor. When you're lifting the thing up, you get this bubble that propagates in, and you get a filament that's always attached to the foot until you pull it up sufficiently high that it can pinch off, and you get left with a kind of a cuspy bit of material stuck to the foot, and the free surface that you will get at the end of this is completely determined by the uplift stage rather than the descent. Yeah?
Is the material always under tension when you pull off and assume no slip? Or in any of these cases, can you just add additional condition that detachment will occur only if the material is under tension?
So that might be a practical way of dictating when detachment occurs. All right? And so in that particular case, you could imagine that the actual scenario of how things happen, it could be a mix of the two ones on the left. Somehow, you do a little bit of a squeeze flow until the pressure gets sufficiently small that you detach. I didn't really want to go into that because the constitutive law that I've been talking about, the constant yield stress thing, it wouldn't be designed for that. But I will say something about that in a second. Okay. So this kind of scenario I think you experience when you're walking in really wet days and really wet mud with Wellington boots. It sticks to your wellies. Okay, so quick summary of this. There's a simple model that you can explore to shed light into indentation and liftoff. Most of the time people completely ignore liftoff, and I think it actually could be quite important. I did it in 2D. You can extend this shallow lubrication type problem to axis symmetry. The important thing is that you get this lift force from the plastic indentation problem. You can generalize it to more Coulomb. Okay, so I did it for this ideal constant yield stress plastic, but you can generalize that to more Coulomb, which is what people traditionally use for certain kinds of granular media. Right? In that case, the yield stress is effectively pressure dependent, and when the yield stress goes to zero, that gives you a detachment condition. So you could put that in order to sort of beef up this idea of detachment. Okay, and what we've been doing more recently is some experiments. So there we are. There's the careful experimentalist. And consider a spherical dinosaur foot. So we've been doing that. There's some sample indentation patterns. This is in sand, measuring free surface displacements and so on. And Thomasina, who's not here, I don't know whether she's made any further progress in relating theory and experiment. That's ongoing. Okay, so finally washboards. Washboard patterns on roads. So this is a phenomenon that you experience in your car. And this is a quote from a reliable source on the web. But the sort of general sort of popular myth about it is that it's something to do with the suspension on your vehicle and the repeated passage of vehicles. All right, so there's a big spring on your car for the wheels, and cars drive repeatedly over the road. That's what causes it. So somehow there's an oscillator there and there's flow past it, so it's a bit like how your vocal cords operate in some other problems. Okay, but that's certainly not the story. So in fact, you don't need a spring. So Jim McIlwain and collaborators, they had a rotating table full of sand. They put a paddle on there. It's at 90 degrees, so there's no spring. And it can move up and down, right? But the degree to which it moves up and down is dictated by the kick that it gets. There's no spring of a fixed frequency here. And if you rotate the drum here fast enough, then what happens is that the paddle starts to go up down and imprint a washboard pattern. Okay, so deformation of the surface is critical. Having a suspension is not. Okay, well, we're talking about these indentation problems, so let me think about this problem in that context. So I'm not purely going up and down now, I'm also moving sideways. So let's think about that aspect of the problem too. You might think of a simple model as follows. Let's take an inclined plate, like in that experiment. It can move up and down, but it's being towed sideways. So what happens when it gets towed sideways is it forms a mound of material underneath in the direction it's being towed, and there's some contact area that's transmitting the lift force. Right, so we've got a depth of penetration and a contact length. Those are two important variables of the model. So the equation of motion of the paddle itself, the vertical equation of motion, is similar to what we had before for the footprint. We've got some lift force. Now it's going to depend upon the depth of penetration, the contact length, and the speed that you're towing at. Okay, so the details of what this is come from something like a plastic indentation problem. Now, for the contact length, you need to balance the masses of inflow and outflow into this mound, and the simplest way to do that is to assume some shape for it. So you can just assume that it's a triangular wedge or something, and then just balances the inflow and outflow of mass. You then can come up with a formula which is basically telling you how the contact length evolves given some function which depends upon the depth of penetration, the contact length, and the speed. All right, so there's a lift force and some conservation of mass function that you can put into this pair of ODEs to explore washboarding. Okay, and what I'm showing you at the bottom here is three solutions of this model with suitably chosen lift forces and conservation of mass functions: low speed, intermediate speed, and high speed. Let me just point out that the one that we're actually using is something like this. You're saying that the lift force is proportional to the contact length and the yield stress, so it's like one of these plastic indentation lift forces. Okay. So the red is the contact length, the black is the depth of penetration. What happens is you speed things up, at some point there is an instability, and the paddle starts to move up and down whilst remaining in contact, but then if you tow it fast enough, it will take off. Contact length goes to 0 at certain places. Okay, so that predicts that if you go sufficiently quickly, you'll get a washboarding instability, and it doesn't really matter what you put in for this, as long as there's some resistive force. It could be a viscous force, it could be a plastic force, it could be a granular force. You should get a washboarding instability. Okay, so we did some experiments to test all of this. This is the setup. We have a paddle that we're going to drag along a granular or a mud surface or something like that. It's pivoted here to allow it to move up and down. Okay, let me just show you a video. Right. So there it is. So it's pretty light, it's well counterbalanced. You pull it along and it immediately starts to bounce. So that was on 1 millimeter diameter glass spheres, and you see a sort of a movie of each bounce. Right, so this is washboarding kind of sand, ideal sand. So here we do it for joint compound. That's a yield stress fluid. It's the stuff that you fill in holes in plasters. This is once again one of the videos of impacts. And at the bottom there, you see the washboard pattern that it generates. Okay, so the experiments confirm that for a variety of different materials, even syrup, you can get things to bounce. Okay, so what's the mechanism? Well, it's related to that wedge of material that you build up underneath the plate. And so what happens is, as you come down and you make contact, there's no wedge to begin with, so you make contact at the original height. But then you build up the wedge, then on the way back out, the wedge is still there, it's decreasing in size, but there's a phase lag. So when you actually leave contact, you end up at a higher position than when you went in. It's desymmetrized in and out by having the wedge there. And that's the mechanism by which you can get instability. It's like having a superelastic bounce. The force on the way up is different from the force on the way in. And you can do a similar thing for just skipping on water. We did it for a skipping problem too. So you might wonder, you know, for washboard roads, what about application? Well, the only message that you can really say is that it should drive slower. That's not very helpful. So there are maybe some other possible applications. This is not a very good picture. This is a ripple pattern that was on a wall like this, and it was in the bathroom at UBC. I saw this nice washboarding pattern on the wall. I felt a bit awkward about standing there trying to get the lighting just right to take a photograph of it. So I had to take a quick photograph and leave the bathroom. So it didn't come out very well. Some of you have seen this before. So you might wonder about other applications. So that was the leisure application. There it is. Popular in California, maybe. And perhaps there's a military application too. Okay. Oh, okay. All right, so I presented 3 problems to you where indenting a plastic material and the force that you get back from it is critical. At the moment, I'm thinking about a slightly different swimming problem when you have a cylinder. So Taylor did a flexible sheet, but he also talked about a cylinder. That's getting more towards the actual practical biological problems of swimming with a flagella or something. And it's very closely related to what we heard from Dan Goldman yesterday. Okay. We're still working on the footprints problem, trying to get a more consistent theoretical description and match it up to some experiments. And maybe there are some other plastic identities that we can explore. Thank you.
I don't think our Australian friends would be very happy with your slightly flippant advice to go slower, because washboarding is a very serious problem there.
Right.
I mean, you must have some more serious ideas. What appeals to me, but it probably doesn't work, is that once in a while you pull a rake behind the truck.
I'm not sure what devices they have developed to do this. I said at the beginning that you know, the suspension is not critical to the development of a washboard, because you could get a washboard without that. And the repeated passage of vehicles wasn't important to you. You could just pull the vehicle once to get the washboard. However, in the practical situation, both the repeated passage and the suspension is important. Right? It certainly reinforces things and makes things worse, and the suspension gives you a sort of an additional thing to control the washboard spating. So, you know, the simple type of model here, I think it's too divorced from the reality of an actual car to really say much about that. You can say go slower, which doesn't help very much. You learn that the inertia of the plate going up and down is important, so somehow adjusting that might be a useful thing. But then, if you really wanted to say something about the washboard road phenomenon itself, you probably should put a suspension in there and get more serious about that.
What sets the wavelengths of the washboard? And couldn't you do some simple scaling analysis to get some sense of what's going on?
We certainly tried that. So in this particular case, this is like a pendulum. You know, especially in the first problem where it was a pendulum at 90 degrees. So that the period, it's just ballistic motion, right? It flips it up, comes back down. So the spacing between the washboard is basically given by how much of a kick it got when it left. Okay, so that's controlled in part by the shape of the surface. You know, I can imagine it's being launched off a certain slope to get to that, and the forces that it's experiencing in each impact. So I remember that we you know, given the forces that involve, you can come up with some scaling in order to figure out what that is. But it's not straightforward, because it depends upon, you know, the initial kinetic energy at the end of a bounce.
I mean, do you know what characteristics would, for example, increase or decrease the wave?
Okay, so I'll tell you a bit of dirty washing then. So we've got that simple model there, right, where you put in some prescriptions for mass conservation of the wedge and the lift force, and there's some physics in there, like the yield stress or whatever. So you solve that, and then you go and compare the predictions with what you see in the experiment, and they're quite different. So that the criterion for the onset of instability is not right. In fact, the model, it's hard to get away from instability. You have to do something really wild to stop it being unstable. Whereas in the experiment, you just tow it slowly, and it's fine. So there's a lot of qualitative differences between the model and experiment, so we kind of abandoned it at that point and decided that, well, the simple dimensionless analysis that we would have made, which would have been based upon that model, is not going to work. So we published the data from a range of experiments that showed how, for example, the wavelength depended upon various things like the towing speed and the weight on the paddle. And there were some scaling laws, but I can't remember what they were. And we didn't have a convincing explanation of it from the model.
In chains, and then we should stop and transition to.
Is there any connection to these washboarding mechanism and pattern to like Shalimach wave formation in soft elastic rubbers with friction?
We wondered about that. So there may be. So in that particular case, when you're dragging a solid object over the surface of rubber, what you find are these waves of contact and slipping that go underneath the rubber.
You see that build up and kind of...
Yeah, I guess I didn't explore that sufficiently to see whether there was a close relationship or not, but it did kind of look similar. Yeah?
James?
There's some, for the classical indentation and squeeze problems, there's some very simple rigid block approximations that you can do, instead of the full slipline solution. They give you reasonable estimates of forces and things.
Yeah, so there's Tazaki, you mean the Tazaki things? So Tazaki had this way of formulating the problem so that you could get essentially the lift force based upon
I don't have an association with a single person, I don't know, but there are some very basic rigid blocks, sort of triangular, rigid plug zones and so on.
Yeah.
I was wondering if you had thought about doing that for the Taylor problem as kind of a back of the envelope estimate of drag forces and things like that.
Well, I guess the result that you get, the analytical result for the swimming speed, is indicative of the fact that there is some stress solution underneath all of that with some characteristic magnitude. So if you were worried about the force that you were needing to exert in order to produce that motion, then you would be able to calculate it from that. And it would be the same as I think what you're talking about. We were interested in just calculating the speed, so we didn't actually look at the force too much, except when we were worried about calculating things like swimming efficiencies. So it went into that. But yes, so I guess the only time that we really used it was in the limit where the swimmer the swimming amplitude was low. So in Taylor's problem, you basically do a perturbation theory expanding around a flat boundary. So it's always a flat punch. And so we used the flat punch solution. But as you say, there are more complicated shapes that one could do. We didn't explore that.
Okay, we should make a transition as well. And while the transition, maybe you can push the question.
Are there rate effects in the stresses when you have the plate dragging across the surface in these in the washboard?
So for the granular case, it's not clear. I mean, there probably are, but
They're not in these.
That's right. You would put some kind of granular friction in there and compute things that way, and it would be rate independent. And same for the ideal plastic. You get a rate independent lift force. But you could do a viscoplastic one where you have a viscous contribution too, and we did that. We had a shallow layer. We redid the lubrication theory for the washboarding problem. So there are rate dependent effects there.
That change, did it delay the onset of instability?
It did. It did.
We find when we're dragging objects, plates at the surface, that there's significant rate effects. As soon as you're buried in the sand, then the rate effects go away. But, but when you're at the surface, it's significant. I'm wondering if it might fix the onset problem.
It might do. You needed some kind of a rate-dependent effect. Yeah.
That's interesting.
Yes. So it did fix it when we were doing the viscoplastic case. We didn't try it for the granular case. But if you could come up with a suitable rate-dependent granular friction there.
We have it. Delivered to you.
Right, let's thank the speaker again. The next talk is coming up. It's by Pasquale Charletta on Curing Revisited, the chemomechanical basis of morphogenesis in soft living matter. Pasquale, whenever you're ready.
Yeah, okay. Does it work? We have to. Thanks again for the invitation. This very nice workshop. My talk will be centered about how actually deformation in solid and in mechanical, from a mechanical viewpoint, ends up with a shape. And so which are the new challenges that this kind of science raises